So geometry class, we are addressing section 17.1 in this learning video. It is on page 241. You can kind of see it there in the bottom right hand corner. We are going to take a look at the concept of dilations, and some of the problems that we're going to use in our notes today are going to come from the book. Some of them we're going to create on our own, but it's really nice to have the graph paper grid on the side, so that's why I'm going to be using our book for the location of our notes. So we're going to start off with these two pictures showing up on page 241. We're taking a look at layout A versus layout B. So the first thing that I want us to address is to remember that the original image is what we call the pre-image, and then the end result after we make a change is the image. So number one says, what are the coordinates of the vertices in the pre-image shown in layout A? Well, let's write down A, B, C, and D. So point A is 0 to the right, 8 steps up. Point B is 6 steps right, 8 up. Point C, 6, 0, because we're not going up or down. And point D is sitting at the origin. Now, it asks us to address the layout of the coordinates for figure B. So I'm going to actually put that kind of side by side. So I've just labeled our pre-image. It's not look quite right, but I'm fixing it, for A, B, C, and D. Now I'm going to label A prime, B prime, C prime, and D prime, because these are going to be our image coordinates. I'm going to do it all in one location so we can see what's going on. Well, A prime, this should have been marked as a prime, is 0, 4, B prime, 3, 4, C prime, 3, 0, and D prime remains like regular D at 0, 0. Okay, well, what on earth is going on? How can we make the connection between the pre-image and the image based on the picture that we see and the actual coordinates? Well, if you guys notice what's happening here in the 0, 8 to 0, 4, we cut it in half. The 6, 8 to the 3, 4, we cut that in half. In fact, we've cut everything in half. So to go from A to B, the pre-image to the image, we are taking half of the original. Sorry, I didn't realize how low down that was on the picture. So we need to express our transformation as a function. So remember how we're going to talk about our pre-image as x comma y, and then our image, we have to say what we're going to do to the ordered pairs. Well, we're literally going to cut x in half and y in half. And what we have just discovered is the concept of a dilation. A dilation is either bigger or smaller in terms of our shape. To be bigger, we're going to multiply by something that is, actually, I don't think I'm going to have quite enough room to write what I want. For a bigger situation, we're going to multiply by a number more than 1. If we want to go smaller, we're going to multiply by a number less than 1. And when I say more and less, bigger, smaller, think positive 1. The negative is actually a reflection. So this is the concept of a dilation. So if we turn the page and we scoot on down to about 2/3 of the way down the page, there we are, on page 242, a dilation is a transformation that changes the side of the figure, but not its shape, by a scale factor of k. The scale factor determines whether the transformation is a reduction or an enlargement. So I'm going to utilize my graph paper space to the left of this definition of dilation. So we need to talk about a reduction. What that means is that our scale factor of k, its absolute value, so just the number, not positive or negative, is less than 1. That's going to make our picture smaller. And enlargement is when this thing called the scale factor, known as k, and again, we're just taking the absolute value, so just the number, not the sign, is greater than 1. So now we need to talk about what the heck is this scale factor and how do we find it. So the scale factor, also known as k, the way that we find the scale factor is we're going to take the prime over the original. So if we back up, I apologize about the bells, I'm doing this one at work. If we back up here and we're like, okay, 4 over 8, that's 1/2. The scale factor that we use when we write our function, that multiplier of 1/2 to make everything smaller, that's what we're going to call k as our scale factor. So our task now is to come over here to page 243, and we're going to talk about some of these examples and then do a couple more, and then probably call it good. This isn't going to be a crazy long video like you guys are used to with me. So 13, we have a triangle with these 3 ordered pairs, and it is mapped onto the primes with a dilation. So for 13a, I'm going to graph a little sketch, hoping I've given myself enough room. We are at 0, 0 for R, we are at 0, 4 for S, and 3, 0, whoops, I graphed my S incorrectly, I apologize. We are at 0, 4, so I shouldn't go right or left, I should go up 4 steps for S, and then 3, 0 for T. So this right here is our triangle. Well, our task now, I'm trying to think what color, I think I'll use blue, is to address a dilation. So for A, 5 over 2 is going to be our dilation. We're being asked, is it a reduction or an enlargement? Well, 5 over 2, if you simplify that to be a decimal, is 2.5. That's bigger than 1, so it's going to be an enlargement. It asks us what are going to be the coordinates of the others. Well, let's sketch this. So if we are taking x comma y and mapping that onto 5 over 2x and 5 over 2y, then when we look at our new ordered pairs of r prime, s prime, and t prime, well, what will we have? Well, if we take 5 over 2 times 0 and times 0 again, we get 0, 0 back. For s, we're going to get 0, and then 4 times 5 over 2, 2 times 4 is, or 2 goes into 4 twice, 2 times 5, that makes 10. So we're actually going to be sitting way the heck up here. I'm going to zoom out a little bit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be S prime, all the way up here at 10. For T prime, we're looking at 3. So 3 times 5 over 2, well, that's 15 over 2, but I'm always a little bit better graphing with decimals. 15 over 2, that is 7.5, and then 0 times anything is 0. So I'm actually going to be off my page. My triangle is going to be enlarged 2.5 times its normal size. So I'm hoping that that makes sense to you, that this scale factor of 5 over 2 is saying we're going to 2.5 times bigger working with our triangle. I'm not going to address part C. I want us to take a look at number 14. Describe a dilation with a scale factor of 1. Okay, 1's just kind of like no man's land. It will have no change. If I multiply my x and my y by 1, I'm using the same x and the same y. There's not going to be any change at all. All right, so we're going to turn the page, or are we? Yeah, we're going to turn the page. I just want to utilize the graph paper grid space that we have for on page 244, and I don't want you to worry about any of the directions that are showing up. I just want us to utilize the graph paper grid space, and we're going to zip through an example. So I'm going to give you guys a triangle, and we're going to go with the numbers 1, 3 for point A. Point B is going to be -2, 1. And point C, let's go with 2, -2. And so I'm going to sketch that right here. Hopefully I've given myself enough elbow room. We're at 1, 3 for point A. B is -2, 1, and C is 2, -2. So here is my not so perfect triangle, but we're good enough. Here's our task. We're going to take x, y, and we're going to dilate about the origin, which means we're not going to move anything else. We can actually have a different center of dilation. And we're going to dilate this by 3. So 3 is k, or the scale factor. So what we're going to have is we're going to have an A prime, a B prime, and a C prime. It's just kind of big because I'm using a highlighter. Maybe this highlighter in blue will be better to see. So our new ordered pairs, we're going to triple what we have. We're going to have a 3 and a 9, a -6 and a 3, a 6 and a -6. So I'm going to have to be off my chart a little bit. We're at 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sitting here for A prime. For B prime, 1, 2, 3, 4, 5. Oh, I'm going to pretend 6 is over here. And up here at 3, there's B prime. For C prime, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I'm hoping that we can see that in a perfect world, this tripled. So I'm hopeful that that is going to click. That's the concept of dilations. The only thing that will be different is maybe you won't have to graph it. Maybe you'll just write your primes, or maybe your task will be to find the scale factor. So again, the scale factor is how does the regular set of ordered pairs change to the new set. In this case, the scale factor was 3. So that's really it. If you guys have any questions, let me know.